You know, for as long as we've had math, the equation has been this pure expression of truth. But what if I told you that for 200 years, there was a problem? A wall, really, that mathematicians thought could never, ever be broken. A problem they just straight up called unsolvable. And that idea right there, that's really at the heart of what we're talking about today. It's a story about a mathematical barrier that stood for generations and the incredible breakthrough that just completely shattered it. Okay, so our story kicks off all the way back in 1824. And for pretty much 2 centuries, a mathematical limit that was set in that year was considered absolute. It basically defined the very edge of what was thought to be possible in algebra. And this led to what a lot of people called math's impossible problem, a dead end that really reshaped the entire field. And this is the wall they hit. It's called Abel's impossibility theorem, named after Niels Henrik Abel. The theorem basically said, look, once you get past a fourth degree equation, there's just no single neat formula to find an exact answer. The problem wasn't just hard, it was fundamentally, officially unsolvable. And you gotta understand, this wasn't some dusty, obscure theory sitting on a shelf. No, this was treated as absolute truth. We're talking generations of brilliant mathematicians building their life's work on the assumption that some equations were just forever beyond our reach. So why? Why was this problem considered a dead end for so long? What made it seem so completely impossible to solve? Let's get into it. The classical dead end. Well, it all came down to the tools they were using. See, the old methods relied on these things called radicals. You know, your everyday square roots, cube roots, that kind of thing. And these tools, they worked perfectly for equations up to the fourth degree. They could unlock them, no problem. But the moment you hit the fifth degree or higher, the complexity inside the equation, which has this cool name, the Gauss group, it just becomes non-solvable. It's like the old keys just didn't fit the new lock. And that forced everyone to just settle for approximations, which, let's be honest, are really just very, very educated guesses. So you can see this created a really clear divide. On one side, you have the classical methods, Abel, Galois, saying, nope, it's impossible. We have to use approximations. And on the other side, you have this new approach, Ezouidi's theorem, that comes along and says, actually, we can get 100% exact verifiable solutions. And it does it by building on totally new foundations, things like recursive structures and hidden symmetries. And this is the crucial part, right? It's more than just a technical disagreement over numbers. It's a total clash of philosophies. The classical view just kind of accepts that there are limits we can't break. But Ezouidi's view, it completely rejects that, rejects this idea of mathematical fatalism. It says, no, every equation has to have an exact answer, just waiting for us to find it. And that philosophical clash brings us to the turning point in our story, a revolutionary new theorem. And the mathematician at the center of all this is Professor Murad Sultan Ezouidi. His whole mindset is captured in this one quote. He's not trying to just tweak old ideas. He's challenging the entire classical framework. So how in the world does he do it? Well, instead of trying to pick an unpickable lock with the same old keys, his method is more like finding a secret panel on the side of the safe. First, it completely reorganizes the equation's internal structure. Then, it applies this chain of recursive transformations. And finally, and this is the brilliant part, it gets the equation's own numbers, its coefficients, to basically generate their own exact roots. It's a totally different way of thinking about the problem. And the result of all this new thinking? The 20th degree equation solved, a feat that generations of mathematicians thought was literally impossible. So just remember, for centuries, anytime you had one of these complex equations, the absolute best anyone could hope for were approximations. You know, getting close was the goal. An exact answer? That was pure fantasy. But Ezouidi's theorem delivers exactly that fantasy. We're talking a complete, exact, and symbolically verifiable solution. And not just for a fifth degree equation, but for a massive 20th degree polynomial. I mean, that's an achievement that just flies in the face of all those classical limits. So this isn't just about one tough math problem. The implications are profound. Let's talk about redefining what can be solved. I love this quote because it really captures the scale of this. It's not just a solution. It could be the dawn of a new era. What it suggests is that the boundaries we've accepted for 200 years, maybe they weren't fundamental laws of math at all. Maybe they were just the limits of how we were looking at the problem. And honestly, that is the most important thing to take away from all of this. It's not just about solving one super hard equation, it's about the principle behind it. The idea that every polynomial, no matter how ridiculously complex, might have an exact symbolic solution just waiting to be found. It completely redefines what solvable even means. Which, of course, leaves us with one last really fascinating question to ponder. If a wall that stood firm for two whole centuries could just fall, then what other impossible problems out there are just waiting for someone to come along with a new way of thinking?